So we just did kind of a little intro to this one yesterday, and we'll get into it a little more today. So what they're doing is they're comparing linear, exponential, and quadratic models. Okay, and so what that's saying is if you have a set of data points, like in a science experiment or something like that, we want to know, can we get sort of a basic idea of what this thing looks like by either using a straight line, an exponential function, or a quadratic function? And we talked a little bit about how this data fits to the curves and what some of the things we need to look for from the data points. And typically it involves the y values or the f of x values, which of course f of x and y are the same thing. Okay. So we did a couple problems yesterday, and we'll get back to them here, but just a quick rundown of what we're looking for. For a linear, we are looking for what they call the first differences. So first differences. I see this thing's going to be writing weird again. So the first differences are the same. And what we're talking about when we say first differences, again, that's like the y values. Do the y values go up by the same amount every time? If they do, then we can use a linear equation for the model. Quadratics is looking for the second differences. And what that means is, so we look at it and we say, okay, well, they're not going up the same amount every time, right? But if you take the differences that we came up the first time, so say like the difference between the first 2 points is 2, the next one is 4, the next one is 6. So they're not the same. But then if you do the differences again, if you go from 2 to 4, that's 2. If you go from 4 to 6, that's 2. So that's second differences. If those are the same, then that's when you have a quadratic model. And then exponential, you're looking for the same ratio of y values. And what that means is that if you take the previous y value and multiply it by some number and keep multiplying by that number, you keep getting the y values that they've given you. And again, I know this is easier to see when we get to the problems. So let's go ahead, and these are the ones we did real quick yesterday. So this one, you looked at your y values. They went from 2 to 6 to 18 to 54. So they're not going up the same amount, right? So that's why the linear one's crossed off. It's not a linear. Then we did the second differences. So we looked here and we said, okay, if we go from 2 to 6, that's 4. If we go from 6 to 18, that's 12. 18 to 54, that's 36. So the second differences aren't the same either. That's why the quadratic was crossed off. So we're thinking it's exponential, but just to make sure, notice what happens here. If I take and multiply 1 by 3, I get 3. If I multiply 3 by 3, I get 9. If I multiply 9 by 3, I get 27. 27 by 3 is 81. So the ratios, what they're saying is basically if you take this number and divide it by that number. So 3 divided by 1 is 3. Then 9 divided by 3 is 3. 27 divided by 3, 3 again. And then finally, we do 81 divided by 27, we get 3. So I see there's a pretty major delay on my pen here today. It's just kind of a pain. All right. So then same thing here. We looked at this guy. We went from 1 to 2, that's 1. Then we did 2 to 7, that's 5. 7 to 16 is 9. 16 to 29 is 13. So first differences aren't happening. But notice this. When I go 5 minus 1, I get 4. 9 minus 5, I get 4. 13 minus 4, I get 4. So the second differences are good. So that means we've got a quadratic. So this is how this stuff works, but that's the stuff we did last time because we had finished up 8.4, and then we went ahead and just did a little intro on these guys because we had a couple minutes left. All right, so we'll go ahead and start working on some new ones here. But it's the same idea. Okay, so we look at this guy. So first differences. This thing was glitchy yesterday too. So we go from 56 to 57, that's 1. We go from 57 down to 50, that's minus 7. Yikes. And then here we go down to minus 15. And this time we're going down, what, 23? It was 23. All right, so definitely not linear, right? So let's look at the second differences. So it looks like we're going down here by 8. And then if we subtract 8 from 7, we get minus 15. And then if I subtract 8 from minus 15, I get minus 23. So our second differences are all the same. That means we have a quadratic. Okay? Questions so far? Okay, thank you, Chloe. All right, let's continue on. All right, so same deal. Look at this guy, so I go from minus 6 to minus 3, that's going to be up 3, right? Minus 3 to 0, up 3. 0 to 3, up 3, and then 3 to 6 is up 3. So our first differences are all 3. So that means this guy is linear. Okay? Okay, so same thing here. So this says, do the data suggest linear, quadratic, or exponential function? Okay, so we can look at this and say, well, this is probably not going to be perfect, but it's probably going to be close. So let's look at this. So we go here. Probably need a calculator for this one. Bring him into the scene here. All right, clear it out. So the first guy, we're going to go from minus 20 up to 17. So we're just going to say, you can just use, say, 20, and then minus 17.5. Okay, so we went up 2.5. All right, so let's check out the next guy. So he went from 17.5 up to 15.1, so 15.1. So that's 2.4. Okay. So that's pretty close to being linear. Let's see if it keeps that pattern going. All right, so next guy. So this one's going to be, let's clear it out, 15.1, and then minus 12.5. So that's 2.6. So we seem to be kind of looking basically linear. So then these guys here is going to be 2.6, and actually it was 2.6. There we go. And then this last one is going to be 2.5. Okay. So one way you could do this, since it's looking pretty linear, right? If we average these guys out, right? I've got 2.5, 2.4, 2.6, and 2.5. If I add those guys together and average them out, so let's do that. So we got 2.6 plus 2.4 plus 2.5 plus 2.5, and then we divide those by 4 terms. So 2.5 is probably a pretty good idea for the slope. Okay. And then notice here we have our y-intercept because they told us when x equals 0. That gives you your y-intercept. So a good possible line for this would be y equals 2.5x minus 20. Well, why did I divide by 4? Because I had 4 terms here. When you take an average, you add up the number of terms you've got. So we added these 4 guys up, and they ended up equaling 10, right? So to figure out the average, I had to divide by the number of them that I just added together. So there was 4 of them. So 10 divided by 4 is 2.5. Okay? All right. So yeah, that's what you do just to take an average. So I was looking at this, it's like pretty much the average change here was about 2.5. It was a little bit higher, a little bit lower. So if we use this, this will give us a pretty good approximation of where we're at. It's not going to be perfect for all of them, but it'll work good for some. So again, if we took, switch up the colors here, and we plugged in 1 for x, I would get 2.5 times 1 minus 20, and that's going to be 17.5, right? And the same thing here. If I plugged in 0, then the 2.5x times 0 is just 0, and I get the minus 20, which is this guy. So next guy will be a little bit off, because if I plug in 2 here, if I do 2 times 2.5, that's 5, and then 5 minus 20 is minus 15. We had minus 15.1. Pretty close, though. So this would be a good approximation of our situation here. Okay. And again, remember, I think, was this class or was it another class? I forget. Some of the classes are kind of similar at times, so sometimes I'm not sure which class I was talking about. But you can look up linear regression calculators online. There's also quadratic regression calculators and exponential regression calculators, and we'll probably be looking up some of those here in a little bit. But for this one, we didn't really need it because it was pretty obvious where we were going. But basically, those calculators, if you look one up and then you would plug in these data values, it would probably give you something about like this. Okay. Let's just go ahead and check out a few more. Okay, so same deal with this one. So let's see what's going on here. So this guy, this is going to be going, looks like down 7. And this guy here looks like it's going to be going down 5. This guy here looks like it's going to be down 3. This guy is just going down 1. So it's definitely not linear, right? All right, so let's check out the second differences. If I go from minus 7 up to minus 5, that's going to be total 2. And then minus 5 up to minus 3 is 2. Minus 3 up to 1 is also 2. This is plus 2, by the way. There we go. So this one looks like it's going to be quadratic. All right. So then what we can do, write down these values real quick, is we could pull up one of those quadratic regression calculators. Did I do that the other day? Was that this class or was that another class? I forget. Do you remember that from yesterday, Chloe? I don't think you were here yesterday, Eli. All right, so I just had to write those down. So I'm going to bring up a quadratic regression calculator, and we're going to plug these numbers in. You'll see how this works. All right, so bring this guy in. And this is all you need to do when you're doing this. Is just Google quadratic, oops, can't spell. As you see, I must have looked it up recently because there it is, quadratic regression calculator. And I took this one that said easy calculation. I said, that's for me. So the way this one works is we just plug in all the x values right here, all the y values here, hit this calculate button, and it'll tell us what our guy's going to be. All right, so our first one, this is easy. We just got 6, 7, 8, 9. All right. Then this guy, we've got 15, 7, 4, and minus. And then we did calculation here. So here's our guy, x squared plus 20x minus 103. And here's what our curve looks like. Let's get rid of our add, thank you. So there we go. All right, so if we grab one of our points here, so we're like at 6, we come up here, and it says minus 19. Well, here's minus 18, here's minus 20, so minus 19 is in between. So there's our point, right? And we do the same thing for 7. We come over here to 7, come up here, it's sitting right at minus 12. Beautiful. And then if we go to 8, come up here, looks like it's between -6 and -8, and that was -7. So this curve is pretty much right on. And the reason for that is, if you go back to what we were doing, now remember in the previous problem, our first differences were a little bit off, right? But then our second distances, or differences, excuse me, not distances, differences here, were exactly the same. It wasn't like one was 2, one was 2.1. So that's why when we did the curve here, it's pretty much right on the money. Okay? But again, that's how you figure out what equation would actually work for this thing. And like I said, I will not bore you with the details on how to do that without a calculator, without one of these calculators, because it is in fact large quantities of no fun. Okay. So again, you can just Google these guys and bring them up. Like say, if you don't like the way one of them works, pick another one. There's a bunch of them out there. Okay. Like I say, I don't know if that first one was good or not. I just saw this thing that said easy. I'm like, oh, okay. We like easy. That's good. Like remember the old Staples commercials with the easy button? Something like that. All right. So let's go ahead and move on. All right. So let's see. There we go. All right. So this one says, use the function shown. Okay. And it says, evaluate each function for x equals 6, 8, and 12. It says, when will function h, so that's this guy, the guy in green, okay? So when will function h exceed function f and function g? Okay. Well, we don't know that yet, but we'll take a look at it. All right, so let's do some number crunching here. So we're going to have the first guy here, and we're going to have x. Get this thing to right, that would be good. And f of x. So we're just going to plug these numbers in. So we're going to have 6, we're going to have 8, and we're going to have 12. This is definitely calculator city, right? So let's do that. Let's bring these guys in. Let's move them over here this time. All right, so our first guy, got enough room? Yeah, we got it. Is 0.75x. So we clear it out. We go 0.75, and we got times 6. So that's going to be 4.5. All right. And then the next one, we got 0.75 times 8. That's just going to be 6. All right, and then the next one, again, we go 0.75 times 12. All It's going to be 9. All right, so that's our first set of guys. I should have wrote that in orange, huh? That would have been the smart thing to do. Anyway. All right, so we'll color code the next guys. All right, so next guy is 1.25 to the x. So this will be x and f of x. I apologize again for the glitchy writing today. It does that from time to time. It gets weird for like a day or two, and then it goes away, and then it's fine. But when it's not fine, it's a real pain in the wazoo. Okay. A little better, but not much. All right, so the first guy, same thing. We're going to have 6, 8, and 12. All right, so let's go ahead and go back here. So clear it out. So this time we're raising to a power, right? So the 1.25, and this raises us to a power, and our first one is going to be 6. So we're just going to kind of estimate this one. This is about 3.8. Okay, then let's try it again. So clear it out. It's got to be 1.25, and then we're going to raise it to the 8th this time. Okay, so that gives us 5.9. Actually, closer to 6. We'll call it 6. 6.0, we'll say. All right, and then one more time. So clear it out. 1.25, and this time we're going to raise to the 12th power. Okay, so that's about 14.6. Cool. All right, so let's look at the last guy then. So again, same deal. We've got x and f of x. All right, so we're going to do the 6, the 8, and the 12 again. All right, so we'll break out our calculator. So clear it out. So this one we've got 0.09375, and then times, this will be 6 squared. So that's 3.375. So about 3.4. Okay. So let's do it again. Pull this one out. So we got 0.09375 times, this time it's going to be 8 squared. So that's about 6. So that's about where these two guys cross. I'll look at the graph here. Oh, the graph doesn't go that far. It just gives us kind of the intro here. All right, so let's do the last one. So then we clear it out. We do 0.09357 times 12 squared. So that's 13.47. Okay, so the second part says when will h, that's the function in the middle in green, when will h exceed functions f and g? Well, it looks like it happens at 12, right? Because at 12, he's at 14.6, which is quite a bit bigger than 9, and it's a little bigger than 13.47. So it would definitely happen at 12. We could check real quick to see if it happens at 11. And we don't even have to look at the first guy. We can just look at the second two guys. So if we did 11 here, let's see where we're at. So we'll do this one first since I've got that color going. All right, so this will clear it out. We go 0.09375 times 11 squared. Okay, so that's about 13, or no, that's about 11.3, excuse me. Oh, because here's what's happening. That's a great question, Chloe. So notice here that it's bigger here than here, right? At 12. What I'm looking at is, does it cross before 12? Maybe at 11. So that's why I'm looking at that. Okay, just trying to be a little more accurate. It definitely passes by 12. I just want to see if it does by 11. Okay, so that means the graph's going out this way. By the time we got to 12, the guy here in green was the tallest. Okay, but I just want to see if it happened before that, if it happened at 11. For this case, no. Like I said, I know for sure that it exceeded at 12, so that's probably the answer they're looking for. And it may be the answer. I just wanted to see if 11 maybe worked. So yeah, I suppose this is a little above and beyond. All right, so then the same thing here. We'll clear this out. So this guy's going to be 1.25 and then raised to the 11th power. So he's 14.64. So 11, he's 14.64. So he pretty much topped out at that point there, right? So 11 points, no, it's 11.64. My bad, not 14. Helps if you write things down correctly. And of course, this thing won't erase. There we go. So it is just a slight bit bigger at 11. So it definitely exceeds at 12. Turns out it also exceeds it at 11. But then, like I said, did they really ask us to do that in this case? No, not really. So 11 would be a little more of an accurate answer, but based on the information they gave us with the 68 and the 12, we could go with the 12. Okay. All right, let's check out a couple more and we'll call it. So it says the function f represents the population in millions of Franklin X years from now. Function g represents the population in millions of Georgetown X years from now. If the patterns shown continue, will Franklin always have a greater population than Georgetown? Explain. All right, so let's see what's going on with Franklin. So if this is linear, then these guys are going to go up by the same amount. So let's see if that happens. All right, so let's move them over here so we can see. So we'll see if the first differences are the same. So let's clear it out. So we got 5.6 minus 3.4. So that's 2.2. Okay. Let's check out the next one here. We do 7.8 minus 5.6, also 2.2. And then the last one is 10. 10, there we go, minus 7.8. All right, so that one's going up linear. So this one's linear. All right, let's see what's going on with this guy. So it looks like we do these guys here, that's going to be 1.2. And this guy is going to be, let's see, 5.4. So 5.4 minus 3.6. So that's going to be 1.2. Wait, hang on. I didn't clear it out right. So 5.4. That's one thing I've noticed about this online calculator. If you don't clear it out, weird stuff happens. So it's going to be 1.8. And then this last one You've got 8.1 minus 5.4. So that's 2.7. So definitely not linear, right? So let's see if the second differences work. So this would be 0.6, this would be 0.9. So it's not quadratic either. So it might be exponential. The way we do that is we go ahead and say, okay, we've got, let's get over here so you can see the numbers. We're going to take the 3.6 and divide by 2.4. So we go 3.6 and then divide it by 2.4. So that's going to be 1.5. Now the question is, if I multiply, or actually I'll just do the division. We'll do it that way. So then if I look at the next guy, so let's clear it out. If I do 5.4 divided by 3.6, that's also 1.5. So this guy's looking like he is going to be exponential. And just to check the last one, do 8.1. So you always do the 1 and then divide by the previous one. 5.4. So yeah, this guy's exponential. So the question was, it says, will Franklin always have a population greater than Georgetown? The answer is no. Because Franklin has a graph going like that, a linear graph, right? Georgetown might start off lower, but since it's going to be exponential, that's going to look like this. It's going to start down here lower than this guy, but eventually it's going to do this. It's going to take off. So this guy is growing at an exponential rate. This guy's growing at a linear rate, and exponentials will always win out over linear. Okay. All right, last one. So it says, at what point will x, or 3 to the x, exceed the other two guys? All right, so this is just plugging in numbers. And we plug in the x values, right? So if we plug in 1 here, that's going to be just 3. If we plug 1 in here, it's going to be 7. If we plug 1 in here, it's going to be 5. So it's not this guy. Let's try the 2 before we do the fancy ones. So if I do 2 up here, so this is going to be 3 to the second power, that's 9. Okay. And then over here, if we plugged in 2, we get 2 times 2 is 4, so that's going to be 9 also. And over here, if we plug in 2 times 2, that's going to be 4, right? 2 squared is 4, plus 4 is 8. All right, so this guy's already been passed up. These two guys are exactly the same. Now, this is where you got to watch how this thing reads. So it says, when does it exceed? Not equal, because at this point they're equal. When does it exceed the other two? So if it's not 2, it has to be something a little bigger. So that's going to be our guy right here. All right. All right, well, that's all I got for you for today. We managed to wrap up a little bit early. All right, guys, we'll do it all again tomorrow.